So hydrogen is a very reactive element, right? And that's why we couldn't find hydrogen is pure form on Earth, because it can really react with most of the other elements, and that's why we couldn't find much or at all pure hydrogen on Earth. So when you allow hydrogen and oxygen to be react, what would happen is that you would release a significant amount of energy, and the good thing that the only product that you form is just going to be water. And the energy released so much that it would be able to fit further reaction and forming a domino effect to keep the reaction going. The good thing about this water forming between hydrogen and water is that they are reversible. And what I mean is that you would be able to convert the water molecule at the lowest energy state back to hydrogen and water at the higher energy state. And this can be done by adding the energy slightly higher than the energy that you would require, that you would acquire from the hydrogen and oxygen reaction. The extra energy is basically just to cover any loss that would be associated during that conversion. So basically, this is the principle of hydrogen production via electrolysis. So you have energy coming in the form of electricity, going to the electrolyzer, split the water into hydrogen and oxygen. And when you need to reuse the hydrogen again, just combine them combine hydrogen with oxygen, and the energy release would be utilized later. And the good thing that water is your only main product, so there's no carbon dioxide emit during the utilization of hydrogen, and that's why hydrogen is termed as the clean energy carrier. And of course, it can only be termed clean only when your hydrogen is produced from renewable sources, as we seen the first couple of slides of my talk. So in terms of energy, we're going to talk first about the specific energy, which is the energy that you would acquire if you say burn a kilogram of hydrogen, or it can either be in megajoule unit, or it can be in kilowatt hour unit, and there's a conversion between the two units. So just a point here, I want to point it out that when it comes to specific energy, the two types of energy that we need to know is it is the higher heating value and the lower heating value, and the difference between these two is the heat of vaporization, which is the energy required to vaporize a liquid fuel into a gas fuel, in this case to vaporize water, from the liquid phase into the gaseous phase. So yeah, in this case, it can be the energy used to convert water to steam. So because of the two different heating value, on the graph on the right hand side, I'm just showing the lower heating value of hydrogen because it represents the amount of energy available to do external work, right? The reason, because when you convert hydrogen and when you react hydrogen with oxygen, all right, either from a combustive reaction or from an electrochemical reaction within a fuel cell, then the water result is going to be normally in a steam kind of thing. So you cannot just take back the heat of vaporization. So showing the lower heating value here would give you an idea of, okay, how much energy is there, would allow you to do external work. So the lower heating value of hydrogen is 120 megajoule per kilogram. Now, you don't need to even know exact the low heating value of other conventional kind of fuel, but you can see that compared to other fuels like methanol, propane, which we use for our barbecue, gasoline, which you run our car, or even diesel, then the low heating value of hydrogen is about 3 times higher than other fuel. In this case, for example, 3 times higher than gasoline. When it comes to kilowatt hour, then 120 megajoule per kilogram is equivalent to 33 kilowatt hour per kilogram. So to give that a bit of perspective, right, the average Australian electricity consumption is about 17 to 20 kilowatt hour per day. So essentially, for a kilogram of hydrogen, it would be enough to power the average Australian household for 2 days. So that would be something very easy to, again, to remember. When it comes to high heating value, this value is 142 megajoule per kilogram, and the difference of 22 megajoule per kilogram here is actually the heat of vibration of water. So the second type of energy I want to mention here is the energy density, or how much energy you can acquire from a volume of fuel, in this case, a volume of hydrogen. And when talking about the energy density, the situation actually reversed, right? So the hydrogen energy density actually like lower compared to other fuel. Doesn't matter which form or which state that you are, putting your hydrogen in, either, compressed hydrogen through 350 bar or 700 bar, or even as a liquid form, hydrogen is much lower energy density when compared to other fuel. And the reason is because it has low density. So that is something that you need to keep in mind, because, for example, if you want to put hydrogen as an onboard storage on the car, then obviously you are limited by the volume of hydrogen storage you can put on the car, right? So you need to be aware of how much volume you have there, and you have to be, choosing the right storage conditions so that it would maximize the energy that can be delivered to that kind of fixed volume. Right. So we're going to talk about hydrogen flammability. And before we go into the nitty-gritty, I just want to show you a very kind of broad concept of what are the requirements for a fire or an explosion to occur. So you need three things. You need a fuel, you need an oxidizer, mostly oxygen, and mix it with the fuel in an appropriate quantity or proportion, and you need a source of ignition. Right. So when it comes to hydrogen, hydrogen obviously is a flammable fuel, because if it's high diffusivity and high buoyancy, it would rapidly mix with oxygen whenever it comes into contact with air. So such contact can come from either hydrogen leaking out of the vessel into the air, or air actually leak into the hydrogen vessel. So you need to be aware of this. And the ignition source normally come in the form of spark, flame, or high heat. All right, so the first property related to hydrogen flammability would be its flash point, right? So this property actually have little relevance to hydrogen gases, because this is the flash point is actually the temperature at which the fuel produces enough vapor to form a flammable or ignitable mixture with air at its surface. So the flash point of hydrogen is at 20 Kelvin or minus 250 degrees C, or in the other is already gas at atmospheric condition, like other gas like methane or propane. So the flash point of hydrogen would have little relevance to its flammability. Hydrogen have a very high auto ignition temperature, right? So the auto ignition temperature is the minimum temperature. Say if you have a hot surface, then the minimum temperature of that hot surface that can ignite a flammable mixture that in contact with it. And now we're trying to barring off the ignition source here, because we talk about it later, but without the ignition source and just having a hot surface, then the temperature of that surface had to reach 585 degrees C to be able to ignite this, flammable mixture of hydrogen that in contact. Of course, that surface had to not have a catalytic effect. For example, if your surface is platinum, then of course you're going to bring down the auto ignition temperature of your hydrogen to very low. So we're talking about a hot surface that doesn't have any catalytic effect to hydrogen ignition and doesn't have any ignition source surrounding it. Then hydrogen mixture can only ignite in a hydrogen air mixture at very high temperature of 585 degrees C. And that's why when we talk about the Joule-Thomson effect before, a rise in temperature 46 degrees is not even enough to bring hydrogen to its auto ignition temperature. So The key takeaway message is that it's difficult to ignite a hydrogen and air mixture just using heat alone. You need to have an ignition source to be able to do that. All right, so the next property I want to mention is about hydrogen flammability range. So we're going to try to define what it is first before we actually talking about the value. So the flammability range is defined based on two values. The first one is the lower flammability level, and the second one is the upper flammability level. So the lower flammability level or limit is the lowest concentration that will support a self-propagation flame when mixed with air and ignite. Right, so that's the definition of it. So if you have a mixture, just fuel and air mixture in general, doesn't have to be hydrogen and air. If you have a mixture of fuel and air, that the fuel kind of concentration in that mixture is below the flammable, the lower flammability limit, then that mixture is a lean mixture. If that's at that condition, there's not enough fuel present to support the combustion. And if you have the fuel concentration that is higher than this upper value, then the mixture is called a rich mixture, meaning that you have too much fuel in that mixture and it's not have, and you don't have enough oxidizer oxygen to support the combustion. So what I mean is that if you have the fuel proportion within that range, within the flammability range, then the fuel and the air are in the right proportion to burn when it is ignited. So I won't give you the flammability range just yet because I want to mention the range. So similar to flammability range, we also have detonation range. And the reason we need to know this range is because detonation is the worst case scenario that can happen for a hydrogen accident. So similarly, it is defined via the lower detonation limit, LDL, and the upper detonation limit, UDL. The definition, for example, for low detonation limit is the lowest gas concentration that will support an explosion when mixed with air, contain and ignite. Now, the key point here is contain. So we're not just supporting the flame, but the flame actually contain and lead to a detonation kind of phenomenon. So any value between this low detonation limit and upper detonation limit would form the detonation range. All right, so that's enough of the definition. So when it comes to hydrogen, the flammability and detonation range of hydrogen is given in this slide. And again, this is a number based on NTP conditions, so normal temperature and pressure condition, 20 degrees C, and atmospheric pressure. Hydrogen, as you can see on the right-hand side figure here, had a very wide flammability range between 4% up to 75% flammability range, much higher or much wider when compared to, say, propane or gasoline. And the detonation range of hydrogen is between 80 and 55 or 59 volume percentage. But just one number that I want to bring your attention here as well is the stoichiometric composition of the hydrogen air mixture. In this case, it's going to be 29.6 volumetric percentage of hydrogen, and the remaining is air. So this a stoichiometric mixture is a mixture when you when you get them to react, both the fuel and the oxidizer is going to be fully consumed. So complete combustion to form this product. There is nothing that is left over. So all of the fuel and of the oxidizer have to be react completely. So that value, when it comes to the hydrogen and air mixture, is 29.6 volume percentage. So it's within the flammability range and detonation range of hydrogen. And the key takeaway message from this slide is that when compared to other, hydrocarbons, like methane, propane, and gasoline, a small leak of hydrogen have a very high potential to burn or even explode. So this is the value of, or this is the range of hydrogen at MTP condition. Just bear in mind that these range actually depending on the temperature and the pressure that your mixture is at, right? So if the temperature rise from 20 to 400 degrees C, then the flammability range of hydrogen and air mixture would increase or expand linearly. The impact of pressure on this range actually is a bit more complicated. You have some decrease when the pressure increase from 0.1 to 5 megapascal, but then it's going to be constant up to 15 megapascal. So what I mean is that the dependencies of hydrogen flammability on pressure is a bit much more complex when compared to its dependency on temperature. But for the time being, it's good to remember that hydrogen flammability range is really wide, between 4 to 75%, and it's have a higher chance of fire and explosion even with a small leak of hydrogen. All right, so we're talking about hydrogen fuel mixture. We're talking about the oxidizer and the composition between hydrogen and air mixture. And the next important thing in the fire triangle is ignition energy. Right? So this is the amount of energy or external energy that must be applied to ignite a combustible fuel mixture. And if you look at the figure on the top here, I probably don't worry too much about all the circle and the line, just focusing on this lowest number. So the minimum ignition energy, which is the lowest energy required to ignite a flammable material in air with oxygen. For hydrogen, this value is 0.017 millijoule, right? This is the lowest energy or lowest energy of the spark that required to ignite your hydrogen when it's in mixture with air or with oxygen. To give an idea of how small this energy would be, I would like to give you an example of the energy that would release when you light a kitchen match and let it burn completely. So if you light a kitchen match and let it burn completely, the total energy that you would release is 1 kilojoule. So have a visual of that 1 kilojoule energy in your mind and try to divide it into somewhere between 500 million to a billion times, right? Then you would receive the energy required to ignite the hydrogen when it is in mixture with air. So when it's that tiny little fraction, like 1 billionth of a kitchen mesh, then it's going to be really difficult to comprehend or to visualize. But the reason for that kind of practice is that I want to emphasize on the fact that hydrogen is really easily ignitable and have very high potential for flame or explosion. And of course, if you compare to other fields, then for example, gasoline here would be in the range of 0.8 millijoule, significantly higher than hydrogen. But even at that 0.8 millijoule, a match of 1 kilojoule energy would be able to ignite gasoline already. So although hydrogen is really easily ignitable, but with a proper knowledge, proper handling, you would be able to handle it in a very safe manner. So yeah, in a couple of slides, it's going to be very technical kind of property related to hydrogen flammability. So this one that I'm showing on this slide is the quenching distance. So this is the maximum distance between two parallel plates that if a flame passed through, it would be extinguished, right? So for the gas that have a very fast burning rate, then this quenching gap actually going to be really small. And for hydrogen, this quenching gap is in the order of 0.54 millimeter. So it's just slightly larger than your half a meter kind of length. And it's actually 3 times less than the quenching distance of our other fuels. And the key takeaway message again is that hydrogen flame are really difficult to quench, right? So even if you spray water onto a hydrogen flame, then you know the hydrogen can actually go around the water droplet and burn around it. So make it even harder to be quenched for that reason. Another property is the laminar burning velocity. So it's defined as the rate of the flame propagation, relative to the velocity of the unburned gas ahead of the flame, right? So this value here just indicates the severity of explosion as a field, and the field that have higher, laminar burning velocity would have a greater tendency to support what a phenomena known as deflagration to detonation transition, or DDT. And I'll explain a bit later at the end of my presentation why this DDT phenomenon is important. But for now, just try to understand that try to remember that the laminar burning velocity can depend on a number of factors, such as temperature, pressure, and the concentration of the unburned gas. But if a fuel or gas have higher burning speed or laminar burning velocity, then it had a higher chance of causing the DDT phenomenon, which we're going to try to avoid. So the value, the hydrogen laminar burning velocity in air vary, as mentioned before, temperature, pressure, and concentration. So the maximum velocity of laminar burning velocity of hydrogen in an air mixture is about 2.44 meters per second when you have a hydrogen and air mixture with 40.1% of hydrogen. At stoichiometric hydrogen air mixture, when you have 29.6 volume of percent of hydrogen, then the laminar burning velocity is a bit lower, but still is about 1.91 meter per second. And when you compare that these two values with the other hydrocarbon, you will see that hydrogen's laminar burning velocity is still much higher compared to most hydrocarbon, which normally in the range of 0.3 to 0.45 meter per second. Now, all of this is due to hydrogen's fast chemical kinetics and high diffusivity. And what I mean is that hydrogen have a greater chance for a transition from deflagration to detonation. All right, so when hydrogen burn, or when you look at hydrogen fire, you will notice that if the fire takes place during daytime, it almost invisible. You can't just detect it by looking at it easily. An example is given on the set of image on the left hand side here, where a comparison of propane flame and hydrogen flame it presents. Right? For propane flame, you can clearly see the color of the flame, but for hydrogen flame, you just couldn't see it, and you can only detect the hydrogen flame when you put it through a thermal imaging camera. In the dark, you can kind of see the hydrogen flame, but compared to the brightness of the propane flame, it clearly like duller, like kind of darker flame compared to hydrogen flame. The hydrogen fire, when compared to gasoline fire, is a bit different because of hydrogen, ability to quickly rise due to high buoyancy and high diffusivity. The hydrogen fire is normally like a vertical fire kind of shape and highly localized. So when you have a hydrogen cylinder ignited in a car, right, then the fire is going to burn away from the car, and the interior might not get very hot compared to that in the gasoline. So, for example, in the two figures present on the right side here, when they deliberately try to ignite the storage cylinder of hydrogen on the left hand side, and the storage cylinder for the gasoline on the right-hand side, and they took the picture. This was done in 2001 at the Department of Energy Hydrogen Program Review Study. They took the picture between 3 seconds after igniting the hydrogen and the gasoline and 60 seconds later. And you can see that after 60 seconds of burning, the car that have hydrogen inside kind of almost being intact, whereas the car that was burning due to gasoline ignition kind of nearly destroyed. And another thing that you would notice from these two pictures is that there's no smoke coming out from a hydrogen fire because, as we know from our previous slide, the reaction between hydrogen and oxygen in air produce, in addition to heat, the main product is just water. So you won't see any smoke or other non-toxic compound coming out from a hydrogen fire. The last property I want to mention in the chemical property of hydrogen is that it's low radiant heat. So what happened is that although the temperature or the maximum temperature of hydrogen flame can go up to 2130 degrees C, but because of the low radiative heat flux, you won't be able to recognize or localize where the hydrogen flame is, and you might not feel the heat emitted from a hydrogen flame until you're almost in the flame, right? So at that point, you're already near the source that can burn up to 2000 degrees C. And this is actually a major problem, when we're talking about detection of the hydrogen fire incident. And case in point, if you look at the imaging on the right side, the fireman actually can get very close to a hydrogen flame with his bare hand without feeling any pain just yet. But it actually really dangerous because you would be in the flame before you even know it.